In this video, we're going to talk about steady-state injection from one side in a semiconductor. So let me take a N-type semiconductor, which is very long, and I'm taking x-axis in this direction, and let's say this is x equals to 0. And as it is very long, I'm not showing you the exact length of the semiconductor. And to have this steady-state injection, let me take at x equal to 0, we want the injection to be present for our analysis. So in order to have it, let me illuminate this side with light so that at this side of the semiconductor, we would have electron-hole pairs generated. And let me take another assumption that this light doesn't penetrate into the semiconductor, which means it generates only the electron hole pairs at the surface or at this side of N-type semiconductor. When the semiconductor was in thermal equilibrium, the carrier concentration would have been Nn0 and Pn0. Now, because of this illumination of light at this side, the carrier concentration is increased beyond the equilibrium state. Let's say the increase at that surface especially is just del N and del P, and we know del N should be equal to del P for charge neutrality reasons. And I'm going to assume that del N is far less compared to the majority carrier concentration in this semiconductor, so that the carriers we are injecting into the semiconductor are very low compared to the majority carrier concentration. We call this low level injection. So in that case, because at this side the carrier concentration is higher, let's say the carrier concentration at that point x equal to 0 will be Pn0 plus del P, the minority carrier concentration, and majority carrier concentration would be Nn0 plus del N. But we can see that del N compared to Nn0 is very small, but whereas del P would be a comparable value with respect to Pn0, because Pn0 is a minority carrier concentration. So let us talk about the hole concentration in this semiconductor, where the hole concentration at this edge at x equal to 0 would be higher compared to far away in N-type. So there would be concentration gradient. As a result, these holes would move to the right side. When they do so, they recombine with the majority present electrons. Let's say with respect to time, we keep the light intensity shining on this side of semiconductor constant. So with respect to time, they would be moving and recombining, and the carrier concentration at steady state would be constant, which means the carrier concentration dP by dt would be 0 in steady state. Now, how do we exactly get how the carrier concentration is inside N-type semiconductor? We need to take the continuity equation for holes. Let me take the continuity equation for holes, which is a del P by del T is given by minus 1 over Q times del Jp over del X plus Gp minus Rp. And now we know Jp is actually Jp diffusion plus Jp drift. So let me substitute that and write the expanded continuity equation where QQ cancel and here QQ cancel. In low level injection assumption, we can say that the gradient is very small so that the electric field gradient can be neglected, and I'm taking it to be 0. And we know that del P by del T is also 0 in steady state. So we can write this expression as 0 equal to dP times del square Pn, the whole concentration in N-type semiconductor, by del X square plus Gp minus Rp. We can rewrite this as del square P suffix n over del X square is equal to Rp minus Gp over dP. And we know that Rp minus Gp is actually the net recombination rate. And we have seen in direct recombination that net recombination rate is given by the excess carrier concentration compared to the thermal equilibrium concentration, which is Pn minus Pn0 over the tau P. And we saw tau P was related to 1 over beta times Nn0. And now let me rewrite this differential equation, which is del square Pn over del X square is equal to Pn minus Pn0 over dP times tau P. And inside the differentiation, having Pn or Pn minus Pn0 wouldn't make a difference. So we can rewrite this as del square Pn minus Pn0 over del X square is equal to Pn minus Pn0 over tau P times dP. Solution to this differential equation can be written as Pn minus Pn naught is equal to some constant, say c, times e power minus of x over a constant L suffix p. And L suffix p is related to dp entropy, where Lp is given by square root of dp tau p, where we're going to call this Lp as diffusion length of holes. And we can rewrite this as Pn. We know Pn would be a function of space. We can write it as Pn of x equal to, we can send the Pn naught to the other side, where this is Pn naught plus c times e power minus of x over Lp. We can draw this function with respect to x as like this, where initial value, let's say Pn, this is Pn of 0. This is exponentially going to decrease as x is increasing, and as x is very high, the carrier concentration would remain at the equilibrium concentration. As we know that these carriers would move to the right side, they recombine with the majority carriers. As we move further into n-type, we would actually see the thermal equilibrium concentration itself. That's why we have this concentration as x increasing, reaching to thermal equilibrium concentration. Now let us find what is C here. So we know Pn of 0 is actually given by Pn naught plus there is a delta P we have. So Pn of 0 is equal to Pn naught plus the delta P, the injected carrier concentration del P. We know at x equal to 0 this is the concentration, so C would be equal to del P. So we can write C as is equal to Pn of 0 minus Pn naught. So let me write the complete function. Pn of x is equal to Pn naught plus Pn of 0 minus Pn naught times e power minus of x over Lp. I can say diffusion length is the most important thing that we found from this discussion. So let us understand what this diffusion length means. So from this function, if you see, the differentiation of this function at x equal to 0, we get a slope. Basically differentiation gives us slope. So the slope is negative, and the point where this hits, the length is called the diffusion length. Or else in other words, we can say wherever this point meets this function, the concentration would have reached to del P is the concentration at x equal to 0, and at x equal to Lp, the concentration would have become del P times e power minus of, we are taking x equal to Lp, so that Lp over Lp would be 1. So we can say the initial concentration would have dropped to 1 over E times the initial concentration when we reach the diffusion length. To understand why the diffusion length depends on dp entropy, so let me take an example where for this graph, let me say dp entropy are fixed. And now for case 1, let me assume dp is increased. In that case, dp basically tells us the ease with which the carriers move in the semiconductor. If dp increases, the carriers would move faster, which means before they recombine, they would have moved extra distance. So as a result, the curve would get changed like this, where it would take longer to have this slope meet this point, where Lp would have increased when dp increases. And similarly, we can say when dp decreases, Lp would decrease. And the same thing with tau p. Tau p tells the average lifetime of holes in n-type semiconductor. So in that case, if the lifetime has increased, let's say tau p is increased, which means the lifetime of holes increased. So they travel more distance before they get recombined. So as a result, the curve would again become in such a way that Lp would increase. So as a result, we can say the Lp depends on both dp and tau p. This analysis is important because we will be using the similar kind of analysis when we are doing diode current equation derivation. And of course, it won't be in the lines of excitation with the light, but it would be a different situation. But still, the derivation would look exactly same.